System software takes a computer task, which a programmer has written in a high-level language, and converts it, using compiler and assembler programs, into the binary machine instructions. Operating systems direct the flow of binary information through the components to control the mechanical operations of a computer. Application programs use the structure of the operating system to provide instructions which result in the wide variety of tasks performed by computers. These programs and the data they need are kept in the computer's memory when they are running. There are 4 basic elements to a computer. Input units feed information to the computer as electrical pulses, which are translated to the zeros and ones. Typical input units include keyboards, mice, and barcode readers. Output units provide the information requested of the computer. They include monitors and printers. In semiconductor memory, there are 2 principal types of circuits. Random access memory stores data that can be easily erased or updated. Known as volatile memory, the data is stored only as long as the current stays on.
Oh.
Come on, Mommy, I want to show you something.
All right.
Read-only memory, known as non-volatile memory, stores information even when the current is off. This memory contains permanent programmed instructions that enable the microprocessor to start. The processor, also known as the central processing unit, is considered the brain of the computer. Millions of program instructions are carried out in seconds, synchronized by a master clock. Inside of this computer, we find a microprocessor containing over 1 million transistors. The speed of a signal traveling through these transistors affects the computer's performance. In an ideal environment where there is no resistance, an electrical signal would travel at the speed of light. In a chip, however, resistance from the conductive paths between transistors and the capacitance of wires and transistors slows the signal speed. Most of the speed is lost, though, on the circuit board, where the signal faces an obstacle course of long transmission lines, inhibiting materials, and the chip's packaging. As the signal travels from one chip to another, it encounters increased capacitance in the large surface areas of the pads, the solder, and the metal leg of the packaging. The most difficult are the thin wire bonds, which resist the flow of current. As circuit technology has evolved, we've seen an increase in the bits of data on which a chip or microprocessor can operate. This increased the computational power, but required more transistors and higher clock speeds. These increases have led to the high-speed chips used in today's powerful systems. With these fast chips, the delay on the board can cause an information bottleneck in high-performance computers. To overcome these problems, this high-end computer uses multi-chip technology to enhance performance. From the back, we see one example of a planar module with the outline of 16 multi-chip units, or MCUs, working together. Each one of these units contains the logic, formally mounted on several much larger printed circuit boards. High-powered chips are packed into these small units, along with the central clock chip that synchronizes with all the MCUs in the system. The board of the MCU is a high-density signal carrier substrate. It consists of 9 interconnected metal layers. insulated with polyimide coating, and fabricated using semiconductor technology. The top layer is used to solder attach all the integrated circuits and connectors. This signal carrier, with its 3,000 to 4,000 solder bonding pads, has been cleaned and prepared for the attachment of high-powered chips. Non-conductive epoxy is dispensed in each of the die side cutouts. The epoxy is filled with microscopic diamond particles which conduct the heat away from the die, while the die remain electrically isolated from the substrate and from each other. Flux is then dispensed to the solder bonding pads of each die side area. When heat is applied during bonding, the flux removes surface oxides. This enhances reflow of the solder. In die bonding, this manufacturing facility uses 3 separate machines to accommodate the 3 sizes of fast chips used in the multi-chip units. The die are bonded to the high-density signal carriers using a chip-to-substrate interconnect called tape automated bonding, or TAB. This TAB chip is densely packed with leads on all 4 of its sides. From the back, we see the inner leads fan out to the outer leads where the bonding will occur.